Guess we should get started. Not sure where everyone is today. Is there something going on?
It's a busy week.
Okay. Are there any questions at this point about homework or anything you covered in the past week? Okay, well, I guess if there are no questions about anything, then we can get started with today's material. And what we're working on today is moving beyond some of the models we've seen for continuous simulation to a kind of model you don't see so commonly in biological contexts, but that I think is a really useful thing to know about in continuous simulation. And that is something called a stochastic differential equation. I'll often abbreviate that SDE. And SDEs are a way that we can get a system that has some of the nice properties of the discrete models we've seen, like a Markov model, so in the sense that it can capture randomness, but it also has the nice properties we've seen of ODEs and PDEs that can describe a continuously varying system. And a nice way to illustrate that is with an example, I think, and the standard example for this is Brownian motion. So Brownian motion is an example of a process that is both continuous and stochastic that helps us motivate why we want SDEs. So if we have Brownian motion of some particle in the solution, then the particle we assume is following some random trajectory. So it's clearly a stochastic process. But it also occupies some point in space at any point in continuous time. So no matter how much you blow up whatever curve we're looking at, you're always going to see the same sort of fractal stochastic behavior. And so we have a system that is both continuous and stochastic. And that's what stochastic differential equations are defined to study. So are there any questions about this yet? Okay, so there's a standard mathematical model of this kind of Brownian motion process that we'll use and it will actually be relevant to understanding how to model a much more complex set of processes. And this is known as a standard Wiener process. And we'll often abbreviate this as W of t. So it's a function of time, but a function of time that has stochastic behavior. So what Wt of t is defined as at any point in time t is a random variable, and then we can think of it as kind of an infinite continuous family of random variables defined for any value t. And it isn't just a generic set of random variables. It has some very nice properties that allow us to simulate these kinds of processes. In particular, there are a few pieces to the definition of W of t that we'll be using. One of them is that we'll simply define an initial condition. So we'll say that at time 0, our Brownian noise process occupies position 0. So if we were looking at this two-dimensional Brownian process, we would probably represent this as two of these W's, so W of x and W of y, and we would just define that the origin is then 0, 0. That one's pretty straightforward. The second one, which is not so straightforward, but is a key assumption of this kind of model, is that for any times s and t, such that 0 less than or equal to s less than t, we have the property that W of t minus W of s is described by a normal random variable with mean 0 and variance t minus s. So this is part of the definition of this kind of noise process. What it's saying is that if we look at the particle at time s and then we look at it again at time t, the distance it's traveled is described by a normal random variable, and the variance of it is proportional to the time that's elapsed. And that's equivalent to saying that this is equal to a normal 0, 1 random variable times its standard deviation, which is the square root of variance, the square root of t minus s. So this is equivalent to saying that in any time t minus s, the particle moves a distance that is square root of t minus s times the unit normal random variable. So does that make sense to everyone? Right, so the final property we're going to need to define this is that for any times st, u, and v, such that 0 less than or equal to s, less than t, less than u, less than v, we have the property that w of t minus w of s and w of v minus w of u are independent. So in other words, over any interval of time, the distance this travels is this normal random variable times the square root of the amount of time it's traveled, but the distance it's traveled in two non-overlapping intervals are independent random variables. So basically what's happened up to a given point in time doesn't affect the perturbation relative to that starting point of what happens next. Does that make sense to everyone? Okay, so this then is basically the model we're going to assume, and as we'll see, just by making these assumptions, we get a lot of really nice properties out of this kind of process that lets us come up with a very simple way of simulating it and actually generalizing to much more complicated kinds of phenomena than just pure Brownian motion. So in particular, this model suggests a way that we can simulate this by thinking about this in terms of, just as we do with other continuous systems, a discretization of the system. So in other words, simulating at discrete time steps, delta t, but simulating in such a way that we're getting an exact model of this particular process. So in particular, these different assumptions or parts of the definition are implying some particular things about how we would do this simulation. This first one is implying that we have some initial conditions. We know how to start our simulation. The second one is implying what we do on each step delta t. So it's saying that if we know where it is at the start of the step, then we know how to perturb it to get it to a properly distributed position at the end of the step. And this last one is basically telling us that we can handle each of these steps independently. We can do one step and then we don't care what happened prior to that step other than where the particle has ended up, and then we can do another step and so forth. And what all of that is getting to is that there's a pretty simple piece of pseudocode we can use to describe this process. If we think of it just in the one-dimensional version for the moment, basically what we're saying is that we get our initial conditions as implied by this step. So x at a time point 0, we give a value of 0. And then we would say for I get 0 to some total amount of time we're trying to simulate t. And then we can divide this by delta t and take -1 to get right number of delta t steps to simulate total time t. Basically all we're doing is saying that x of I plus 1 is x of I plus square root of delta t times the normal 0, 1 random variable. And this then is the pseudocode for simulating one-dimensional Brownian motion that follows from this model. But this would basically be an exact simulation of the model as described here, as long as we're only looking at these delta t time steps. But if we wanted to look at finer resolution, you could shrink the delta t time steps, and it would still be an exact representation of the random process described here. Just whatever delta t you use, the amount of time you're going to need to simulate it is going to grow with 1 over delta t, the amount of steps of simulation you need. Does that make sense to everyone? Okay, so that gives us a simulation of one-dimensional Brownian motion. And it's pretty straightforward if we wanted to do this two-dimensional model that I've drawn here. So we could say pretty much the same thing. We could say that maybe we've got an x0, x0. We can also say there's an independent y0 that's initialized to 0. We could say that we've got, again, I get 0 to t over delta t minus 1. And then we could just say side by side, xi plus 1 gets xi plus square root of delta t times 0, 1 normal random variable. And yi plus 1 gets yi plus square root of delta t times an independently 0, 1 random variable. And then that gives us a simulation of two-dimensional Brownian motion. And it would be the same thing if it were 3 dimensions. We just throw in a z term here, and we've got a 3-dimensional model. You could also generalize to handle multiple particles. So if we wanted 1,000 particles moving according to Brownian motion, we just repeat this 1,000 times, so 1,000 different x and y variables, and then run through 1,000 different independent normal samples on each step, as long as the particles don't interact with one another. As soon as they start interacting, you start running into problems, because then your random variables start becoming correlated. But we can at least get this far with this basic kind of pseudocode. So does this make sense to everyone? Any questions at this point? Okay, so that is still kind of limited, though. So very often what we'll want to simulate is not these independent particles moving independently in each dimension, but the basic tools that we get to this point in the simulation actually give us more or less what we need to come up with a much more general kind of model. And the way we can understand that is by noticing that what we do here is actually very similar to what we do when we're numerically integrating a differential equation. It's very similar in particular to the pseudocode for the forward Euler method with some modifications. In particular, if we were simulating a deterministic system, just a deterministic ordinary differential equation, say, then we would have something of the form dx dt equals f of x, which would be the system we're trying to simulate. And we would have equations of the form x sub n plus 1 equals x sub n plus delta t f of x sub n. That's just a statement of the forward Euler method. And we can kind of simplify that a bit to think of this as being x sub n plus 1 equals x sub n plus, we'll just abbreviate this thing as dx. So basically what the forward Euler method is saying is that we get the next value of x by taking a small perturbation in x dx, which happens to be delta t times f of x at that point. That's basically the perturbation in x. And what we're doing with this pseudocode here is something very analogous to that. We're saying in the stochastic case that x sub n plus 1 is equal to x sub n plus now a dw term, where w is a perturbation in this Brownian noise process, or perturbation in this kind of continuous stochastic process. And once we recognize that, we have this dw term, which in this case is going to be represented by this square root of delta t times this normal 0, 1 random variable. We can recognize that what we're doing here is very analogous in the deterministic and the stochastic case. And a lot of the theory we use in the deterministic case, we can actually generalize to apply to the stochastic case. So, in particular, we would often say in the deterministic case that if dx dt equals f of x, then that means dx equals f of x dt, and that in some sense means that x is the integral of f of x dt. And we can similarly say in the stochastic case with the right definitions that if we put things more or less in this form, then we can say that there is some dx, which is equal to maybe some g of x times this dw term. And what we're really trying to do here is integrate with respect to that dw. So basically we're saying x is the integral of g of x with respect to a noise term w. And that's kind of an odd concept, integrating over noise, but in terms of what we do computationally, that's exactly what we're doing. We're integrating over this Brownian noise process. And if we recognize this as integration, we can realize that what we can do here can capture a much more general set of phenomena. In particular, phenomena where we might have arbitrary amounts of noise, maybe as functions of x and t, and maybe non-noise terms that we can throw into the same kind of equation and come up with a more general kind of model, as we'll see in a moment. And what I'm trying to get at here is that we can bring in a lot of the tools of numerical integration to these stochastic processes using a concept known as stochastic integration. So stochastic integration is defined a few different ways. It's not as simple a concept as ordinary deterministic integration, but we'll use one basic version of this known as an Ito integral. And an Ito integral is basically just a way of defining what we mean when we integrate over a noise term. And in particular, the Ito integral is defined as the limit delta t goes to 0 of the sum j equals 0 t over delta t minus 1 of x of j delta t times w of j plus 1 delta t minus w of j delta t. And then this thing is simply an approximation to x of t that gets arbitrarily good as delta t goes to 0. And this thing is our approximation to dw of t, the random noise process, which also gets arbitrarily close to the true continuous Brownian noise thing as delta t goes to 0. So that is equivalent to sum j equals 0 to t over delta t of x of j delta t, square root of delta t, and 0, 1. That should be minus 1 there. So in other words, this thing we already know is square root of delta t times the 0, 1 normal random variable, so unit normal. And this is simply the definition of what we mean by an Ito integral, or what we mean by integrating with respect to w. And once we establish a definition like this, then we can basically apply all of our tools of integration using, instead of the limit of delta t going to 0, using some finite non-zero delta t to get an approximation just as we would with any continuous integration problem. So that makes sense to everyone so far? So I should say that there are other ways to define a stochastic integral. It doesn't really matter which definition you pick. So the Ito integral is one of them. There are other ones. But as long as you pick one and you're consistent about it, everything kind of works out. So we'll just use this one in this class. And what this lets us do is, once we recognize what we mean by integrating over a noise term, is combine terms where we can talk about integrating some x as a function of t, which has components of both the deterministic function, let's say f of x of t, and f may itself be a function of t, times a deterministic dt. So if we stopped here, we would just have a dx dt equals f of x function. But also throw in a g of x of t, and g also may itself be a function directly of t independent of x, times one of these noise terms. And this is what we mean by a stochastic differential equation. So that is an SDE in the general term. And we could have multiple independent noise terms. So if we were trying to integrate over multiple different noise processes, we could have a g1 of x of t, comma t, dw1 of t, plus g2 of x of t, comma t, dw2 of t, and so forth, to integrate over multiple independent noise processes. And what we want to be able to do is pose systems in terms of this kind of stochastic differential equation, and then numerically integrate those systems similar to what we've done before. So I think this kind of thing gets much clearer with an example. So let me propose an example of where we might be interested in using a stochastic differential equation model. So let's suppose we're looking at maybe the surface of a cell, and it's got a protein bound in it, and this protein has some arm that sits off in solution, kind of flops around, and we're interested in the position of the end point of this arm. So maybe we want to know how often that's a certain distance away from the cell or whatever. So that's something we might model with a deterministic part and a stochastic part. So we might say that there is a stochastic part because there is a Brownian noise acting on the end of this, so just kind of trying to randomly move around in solution. But we can also say that this tether piece imposes a deterministic restoring force that pulls it back to the cell, and we can model that as maybe a Hooke's law spring, so say that it restores with some force minus kx, pulling this back towards the surface of the cell. And then what we're interested in doing is coming up with a way of simulating this where we're assuming there's some Brownian noise, and let's say we've got some constant d on that noise, we've got a dw term moving this stochastically, and we've got this deterministic force restoring it. So is the problem clear to everyone? Okay, so if we pose this way, then what we would want to do is, first of all, state what we're trying to solve here. So state what system we're trying to simulate. And for a stochastic differential equation, what we would generally assume is that we're trying to come up with a statement of dx, of the instantaneous change in x, and that is going to be a function, typically we're going to assume an additive function of a stochastic component and a deterministic component. So if it were just a restoring spring force, you would say that dx is equal to minus kx dt. And this would be equivalent to saying dx dt equals minus kx. That's just normal equation for the action of a spring. But we also want to throw in this constant d times a noise process, which is going to be the Brownian noise that's randomly perturbing this in concert with the spring force pulling it back in a deterministic way. And this could itself be a function. This could be a d that maybe varies as a function of x, so maybe there's a stronger Brownian force when it's farther from the cell. But let's just say for the moment it's a constant d. So is this statement clear to everyone? Okay, so we've pretty much seen what we want to do to simulate this kind of system. We would start with some initial conditions. Let's say we'll give this some value x of 0, gets x at its initial point 0. And then pretty much all we need to do is say y gets 1 to t over delta t minus 1. So just like we had before, iterating over discrete time steps. X of I, we'll say, gets x of I minus 1. And then we would put in, for the deterministic part, exactly what we would do in the forward Euler case. So if we were simulating just the deterministic part of this by forward Euler, what would we put here? If this were just deterministic, we would have the equation dx dt equals minus kx. So what would go here is delta t plus dx dt at point I minus 1. So what we're going to get here is minus k delta t x of I minus 1. So that's going to be the deterministic part. And because integration and differentiation are linear operators, all we need to do then is add in the stochastic part, and we'll get a correct simulation. So if this were just a simulation of the Brownian process, what would we put here? For what would be the perturbation we apply to xi minus 1 to get xi? Well, this is basically what we had seen previously. What we would want is a perturbation of the form square root of delta t times the normal 0, 1, and then we have a scaling constant here, so we need to throw that in. And if this d were a d of x, then we would just throw in d of x evaluated at point I minus 1. And that would give us the perturbation for handling this noise term here. So if d of x were, let's say, d times x, then this would be d times xi minus 1. And this then would be a simulation of this particle tethered to the cell. And what we would see is that we would have a Brownian fluctuation, but this spring would keep restoring it close to the cell, so it would never get too far away. And if you look in the text, you can see an illustration, so a plot of what we get from simulating this process, and you can see how that compares to what we get from a simulation of the untethered system, so how those differ from one another. So are there any questions about any of this yet? Okay, so I think the key thing to observe here is that we've got a simulation method where basically all we're doing is combining a standard forward Euler simulator with a standard Brownian simulator, just combining those additively for a particular variable, and that gives us a simulation of the stochastic differential equation. Or in particular, it's a numerical integration of the stochastic differential equation. And this particular combination we refer to as the Euler-Maruyama method for numerical integration of stochastic differential equations. So just do the forward Euler for the deterministic part and do the square root of delta t and 0, 1 times the magnitude of the noise for the Brownian part. All right, so any questions about any of that? So in the general case, we'll want to see how this applies. And it's pretty much the same thing in the general case. So if we had some arbitrary function, let's say dx equals f of x and t dt plus g of x and t dw, and maybe I'll make it even more general. So we'll say that maybe we've got multiple noise processes. So we've got g1 x of t dw1 plus g2 x of t dw2 and so forth, then all we would need to do to simulate this in the general case is to say that we basically take a for loop like we have in any of our numerical integrators, and then within the for loop we'd have the equation xi plus 1 gets xi plus the forward Euler term, so f of xi and, well, you can say ti, but that would be delta t times I times delta t, and then each of the Brownian terms. So we would say that we would have g1 of xi, I guess, yeah, that's right, so xi times delta t times I, and what should we put here? So what do we multiply this by?
Square root of delta t and over.
Yeah, so square root of delta t times the normal random variable. And then if we have more of these noise terms, we would just keep adding those in. We could have g2 xi delta ti square root of delta t independent, normal 0, 1 random variable, and so forth. So does this make sense to everyone? Okay, so let's see another example of where this kind of thing might come up. So one place we might be interested in using a stochastic simulation is, let's say we're looking at a model of a chemical reaction system. So we've seen various ways of simulating chemical reactions. Maybe we've got a reaction, A plus B goes to C with some rate constant K. So in the deterministic case, what we would have is you start with some starting amount of A and starting amount of B, then those are going to kind of fade away over time, and we're going to have some C that builds up over time. So we know more or less what that's going to look like. But let's suppose we're looking at a relatively small volume of simulation. So we don't have too many copies of the molecules A and B, which you might see if you were simulating, let's say, one cell. If you're looking at one cell, and these are proteins in the cell that have to react in some way, maybe you've got 100 copies of A or 1,000 copies of B. What you're going to see is some stochastic noise in this kind of system. So what the mass action differential equations we've seen before are saying, so the equations like dA dt equals minus KAB, what these are doing is really describing an average rate of consumption of the molecule A as a function of K and the amount of A and B. But if you have a small number of molecules, this average is going to have some variation to it. In any given amount of time, maybe we've got a little more than KAB reaction events or a little fewer than KAB reaction events. And that's something we might want to describe with a noise process. So let's suppose we take this standard mass action model, and I'll rewrite it as dA equals minus KAB dt, and dB equals minus KAB dt, and dC equals plus KAB dt. That's just a standard set of mass action differential equations. And then we'll propose that there is some stochastic variability in the system. Now, one of the things that's a little tricky in thinking about these models is that you have to model your noise just as you would model other parts of the system, and different assumptions about what the noise is supposed to be doing will lead to different mathematical models. So in the textbook, I put one version of a model here, where I think I had assumed that the noise would have the form, say this one would have a noise term, the form Ka times a dW1, or kappa B times dW2, kappa C times dW3. But for here, let's throw in a different assumption. So take these out, and we'll say that suppose we are trying to simulate noise in reaction events. So on average, in any unit of time, KAB reactions occur, and each of those reactions consumes an A and B and produces C. But let's suppose that sometimes instead of getting KAB reactions, you get KAB plus 1 reactions, or KAB minus 2 reactions. So what would that mean in terms of the noise processes acting on these different equations here? Let's say we knew that the noise was 10 in the first equation. What would that tell us about the noise in the second and third equations on a particular time step? Let's say there were 10 extra reactions consuming A in this equation.
No, it's be 10 more in B and C.
Yeah, so if we had an extra 10 reactions consuming A here, that would mean that we would have a noise term of minus 10, and that would tell us we also have to have a noise term of minus 10 here because the same number of Bs are consumed, and we have to have a noise term of plus 10 here because that's how many extra Cs are produced. So to model that, we need a somewhat different assumption where instead of having 3 independent noise processes, we would say that we have one noise process that contributes to all 3 of these. And a typical way of putting that might be to say that we would have a noise process that takes the form square root of, say, KAB times dW here. And what this is saying is that we would have a noise process where the standard deviation of the noise is equal to the average number of reactions. So for a reaction system, that would actually be a reasonable thing to put because reactions are, we would generally assume, more or less a Poisson process. So the standard deviation should be about the square root of the average number of reactions. And then we would throw in exactly the same noise term here. So plus square root KAB dW, and subtract that amount of noise here, minus KAB dW. Now, since these are zero-centered normals, half the time this is going to give you a negative value, and then this would be negative, this would be negative, this would be positive. The other half of the time this will be positive, and then this is also positive, and this is negative. But basically this gives us a model of this kind of noisy reaction system. And again, it's going to be a different model than if we had assumed a different representation of what noise is doing in the system. So does that make sense to everyone? Okay, so let's say we've now got that model of the process we're looking at. Let's come up with a simulator that would simulate this reaction system. So if we want to simulate this, the first thing we need to do is initialize our system. So we can say there's some A0 and B0 and C0, and let's just say we'll assume that this is given to us by a problem or by our user or whatever. And then we're going to have some kind of for loop. So for I gets 1 to t over delta t. Then if we want to simulate this process, it's going to be a little different than what we saw in our previous simulations because we need to pick the same random variable for each of these. So what we're going to do is start by just picking that random variable. So let's say z gets something sampled as a unit normal random variable. And then we would want to attribute that z to each of these individual equations. So we would have an a sub I gets a sub I minus 1, and then what do we add to that? We've got first the deterministic part. So what do we put down for the deterministic part of this model here? We've got a k-a-b dt term. So we do this just like with forward Euler. We would say we get minus k, ai minus 1, bi minus 1, delta t. So that's what we would have if this were just a forward Euler deterministic simulation. And then what do we put for the stochastic part? Yeah, so plus square root of k, ai minus 1, bi minus 1, and then we have to multiply that by square root of delta t and by z. And then we would do the analogous thing for b. So bi gets bi minus 1 minus k, ai minus 1, bi minus 1, delta t, plus square root of k, ai minus 1, bi minus 1, square root of delta t times z. And again, it's important for this model that it's the same z here. We're just sampling it once. And then we would do almost the same thing for c. So ci gets ci minus 1 plus k, ai minus 1, bi minus 1, minus square root of k, ai minus 1, bi minus 1, square root of delta t, z. And this then would give us a simulation of our stochastic reaction system that's going to look, instead of like the relatively smooth curves there, we would see something like if we had some starting amount of A and starting amount of B and starting amount of C, this would kind of fade away, but with some noise to it, and this would also kind of fade away in a noisy way, and then this would grow in a noisy way, and we get something like this. So does that make sense to everyone? Right, so this particular model, I posed the noise here in a way that we would have conservation, so whatever extra molecules are created by the noise, an equivalent set of molecules are consumed by it. So basically we're kind of conserving the total mass in the system. Other noise models wouldn't have that kind of property, and you might end up with something where this could kind of drift off to infinity. But in this, worth noting that this is not really entirely a realistic simulation of how this kind of noisy reaction system would behave. So can anyone think of why this might be unrealistic for some purposes? thing we could notice is that if we get to the point where b more or less should have gone to 0, it's actually possible for it to go a little negative in this kind of model. Shouldn't go too negative, because then it would kind of push the system back the other way, but you can have some unrealistic behavior there. We'll see next time how, if we're going to small enough limits, you can actually use a different kind of purely discrete model that would give you more realistic handling of this kind of behavior. But basically, this is a pretty good kind of model for handling kind of medium scale chemistry. So things that are maybe not like one or a few molecules, but are also few enough that we have to worry about stochastic variation in the system. All right, so any questions about any of that? Okay, so that is basically the main way we will look at to simulate stochastic differential equations. And I hope these models illustrate that you can be very general with regard to these kinds of systems. So almost any kind of deterministic differential equation you can think of, you can come up with ways of making it a little more realistic or a little more appropriate for some purposes by adding noise terms into this. You can also do this with partial differential equations. So you can talk about noisy diffusion, for example, if you want to have noise variation within one of those diffusion systems that we've looked at, where the amount of particles at a given point in space fluctuate based on the amount near it, but basically lots of variations on this. All right, so these kinds of models are useful, but they are much harder to analyze than the deterministic models we've seen. But I do want to go through a little bit of the theory behind these and how we would use that. So what I've shown you here is not the only scheme you can use for numerically integrating stochastic differential equations. It's kind of the equivalent to forward Euler, the simplest, easiest thing you can use. And there are whole families of these, so stochastic kind of versions of the Runge-Kutta methods and the other ones we've seen if you want more accuracy. But the theory behind them is a lot more complicated. But I do want to walk through at least how to do some pieces of the analysis we've looked at before for things like analyzing stability of a system like this. So there were two properties we looked at when we looked at deterministic numerical integration schemes. So two properties we used to characterize the behavior of a scheme. Does anyone remember what those were? Lloyd? So let's say, why might we prefer midpoint method over forward Euler? What's the property that is better about midpoint than forward Euler?
Accuracy?
Yes, it has better accuracy. And why might we prefer, in some cases, backward Euler to forward Euler? What property does backward Euler have that's nice?
Less likely to blow up.
Yeah, so it's stability. The two properties we usually worry about are accuracy and stability of these schemes. And both of those are more complicated questions when talking about stochastic systems than deterministic systems. So I'm not going to go through how to analyze the accuracy, because that gets really messy, but I just want to say a few words about even what we mean by accuracy in a scheme like this. Because even if we had, let's say, one of these Brownian motion models, and we had the actual system and a simulation of that system, they might be doing completely different things, but the simulation might actually be a perfectly accurate model of the real system. So you can't just run the real system and run the simulation, see if they do the same thing, and say, well, if they do the same thing, you've got an accurate model. If they don't, you don't. Because even a perfectly accurate Brownian motion model is not going to do the same thing as as an actual Brownian motion system. And what this is getting at is that we need to come up with some more sophisticated sorts of definitions of what we mean by accuracy. And there are really two definitions we would widely use. And the one that's usually more relevant to us is what's called the strong order of accuracy. And the strong order of accuracy we define to be a value gamma if the following is true. Let's say we define the real system as x of t sub n at any given time point n. This is the real system we're trying to simulate. And we define the simulation of it as x sub n at the same time point. Then we say that the simulation has strong order of accuracy gamma for the real system if the expected value of x sub n minus x of t sub n is less than or equal to some constant c times delta t to the gamma. Right, so let's say we were looking at a purely deterministic system. So suppose we were simulating a purely deterministic system and we used the leapfrog method. What value would this give us? What would be the strong order of accuracy of leapfrog, let's say? Well, if it's a purely deterministic system, the strong order of accuracy is exactly the same thing as we usually mean by accuracy. So there's nothing to take an expectation over. It's just completely defined. The error is going to be delta t to the order of the method. So for leapfrog, delta t squared, because it's a second order method. So if you apply this definition to a deterministic system, the strong order of accuracy is just what we mean by the accuracy. It turns out that this can be quite a bit worse for a stochastic system, though. So if you had, let's say, just a particle sitting at point 0, so it never moves, and we try to simulate that with a Brownian motion model, then we would expect that the Brownian motion model would diverge from the origin of the system at a rate of square root of delta t. So essentially the amount of time it diverges is going to be related to the square root of the time we're watching it. And because of that, we end up with more or less getting a divergence in the order of accuracy that is actually fractional. So if we take this definition, apply this to the errors we accumulate in this Euler-Maruyama method, basically what's dominating the errors are these square root of delta t terms. So we actually end up with that the Euler-Maruyama method has strong order of 1/2. So that is a pretty bad accuracy for these kinds of methods. It basically means that if you shrink the step size by a factor of 100, you reduce the error in your simulation by a factor of 10. So generally, you need to take pretty small steps with these kinds of simulations to get a reasonable model of your process. There's another definition called the weak order of accuracy. And the weak order of accuracy is defined to be gamma if the following is true. If the expectation of the simulation xn minus the expectation of x of t sub n, so the expectation of the real process, is less than or equal to c delta t to the gamma. And so let's suppose we are looking at a real process that is just continuously sitting at 0, and we simulate it by a Brownian noise process that is diverging with some Brownian, some random normally accumulating noise. What would be the weak order of accuracy of that simulation? Well, basically, it would be infinitely accurate. So if we had the true process with no noise in it, and then we simulate something that has the same mean, but with noise thrown on top of it, then the difference between the expectations is 0. So we would say that that's a perfectly accurate process, which obviously isn't a very reasonable definition in general. But that's what we would get out of this. What if we were looking at a purely deterministic process and we ran the leapfrog method on that? What would be the weak order of accuracy of leapfrog integration? It would still be 2, just like with the strong order of accuracy. So for a perfectly deterministic process, you'll actually get the same behavior, gives you the same definition as with as you would get from the standard deterministic order of accuracy for a deterministic process, regardless of whether we use the strong or the weak order. But for a stochastic system, these can be quite different. And actually for the Euler-Maruyama method, we have a weak order. Well, can anyone guess what the weak order would be? Well, effectively what we're doing is kind of averaging noise out of this, and if you throw out the noise from these systems, you're just left with forward Euler. So the weak order is going to be 1. Basically, it's kind of taking the noise out of the question of accuracy, and then it's just forward Euler, so you get the forward Euler accuracy. So does this make sense to everyone? Okay, so again, I'm not saying how to derive this. It's really complicated. There's a whole subject of stochastic integration you can get into, and there's a theory of stochastic Taylor series, but it's a lot more complicated than the usual deterministic Taylor series. So basically, if you really want to know, you can take classes on this. I think the math department here offers a series of classes on stochastic calculus that you can take, but it's complicated. It's the best answer I can give now. There are methods that give you better accuracy than this. So one example, just to show what a higher order method would look like, is what's called Milstein's method. And Milstein's method looks like the following. It says x sub n plus 1 is x sub n plus delta t f of x sub n, where f now is the deterministic part, plus g of x sub n, which we're assuming is the stochastic part, square root of delta t times a normal random variable z, plus a correction term, 1/2 g of x sub n, g prime of x sub n, times square root of, times delta t, z squared minus delta t. So basically throwing in this correction term gives us an improvement over this part, which would basically just be the standard Euler-Maruyama method, and that turns it into strong order 1 and weak order 1. But again, I'm not going to try to prove why that is the case. I'm not actually sure myself why this would give you strong order 1, but this is a strong order and weak order 1 method. Okay, so any questions about any of that? Okay, so the other thing that we would want to analyze typically is the stability of the scheme, and we can analyze stability of stochastic systems just like we could deterministic systems. And stability is also a trickier concept because even if we have a process that on average has a value of 0, so let's say pure Brownian noise, the average position of a particle under Brownian noise is always 0 at any time. But at the same time, that would be an unstable process. So if we start a particle at the origin, it's going to be moving around some random process. At any point in time, if you average over all of the possible trajectories, its average position remains the origin. But we expect it to drift away from the origin with some distance that's about the square root of the amount of time we've been watching it. And so we would say that this is an unstable system, even though the mean of the system, the deterministic part, is stable. And so we need some more complicated kinds of theory, a more complicated way of describing stability to talk about what it means for a stochastic system to be stable. And it ends up that a decent definition is to say that a system is unstable if W of t squared, because it's easier to define than stable. Stable if the expectation of the noise process squared is some constant, or in the limit as t goes to infinity, approaches some constant. So basically, in the Brownian noise process, the expected value of the position is always 0, but the expected value of the position squared grows with the amount of time we're looking at. So for a pure Brownian noise process, the expectation of Wt squared is actually t, so the limit as t goes to infinity, this goes to infinity. But if this went to a constant, we would say that that is a stable system. So does that definition make sense to everyone? All right, so that's what we mean by stability in a stochastic system, but we would then want to come up with some way of reasoning about whether a particular scheme on a particular problem is stable. And the way we would do that is very much like what we do with a deterministic system. We come up with a test function and see how the system behaves on that test function. So what test function did we use to characterize stability of deterministic systems? This is what I referred to as von Neumann analysis. Well, to study stability of a deterministic scheme, what we do is assume we've got a function of the form e to the omega t, and then we see how that function would behave, and then we characterize stability as a function of omega, where we assume omega is some complex constant. And that's how we describe the stability of a scheme. So typically we would be talking about, in the complex plane of omega, what values of omega, and really omega times delta t, lead to stable, unstable, or semi-stable behavior. And in a stochastic system, we do something a little more complicated. So in the deterministic one, e to the omega t means that dx is equal to omega, or well, dx dt is omega x, which is equivalent to saying dx is omega x dt. And we do something kind of similar in the stochastic case. We say that dx is equal to omega x dt plus mu dw, where mu here is now a noise parameter, so we would assume this is some positive real constant. Omega is still a complex variable, and then you don't have quite as simple a characterization as just plotting it in the complex plane for omega. You have to think of this in terms of omega and mu, and where that is stable, unstable, or semi-stable behavior. But just as we have some basic guidelines that tell us what behaviors are stable in the real system, we can get some analogous ones that are slightly more complicated for the stochastic system. So in particular, in a deterministic system, we know for the real system what values of omega should correspond to stable, unstable, and semi-stable behavior. So in a real system, what values of omega correspond to a stable system? Well, a real function e to the omega t is stable if omega is negative. And then it's unstable, so that would be stable. It is unstable if the real part of omega is positive, and it is semi-stable if the real part of omega is exactly 0. So if omega is purely imaginary, you get something that oscillates. So e to the I omega t for real I is an oscillatory function. So does that make sense to everyone? All right, so in the stochastic case, we get a very similar characterization that the system is stable if the real part of omega plus a random perturbation 1/2 mu squared is less than 0. So basically, you can kind of think of this as meaning that pure noise or pure Brownian motion process is inherently unstable, and you have to damp it a little bit to get back to stability. So this has to be a little in the negative, and the amount by which it has to be negative for the whole thing to be stable is 1/2 omega, or 1/2 mu squared. And then we can equivalently say if the real omega plus 1/2 mu squared is greater than 0, you get an unstable system, and then a semi-stable stochastic system would be basically what we get if that's exactly equal to 0. So basically you have the deterministic part exactly balancing the instability introduced by the noise part. So does that make sense to everyone? Okay, so that's telling us what the real system would do, but we would then want to know what the real system does, or what the simulated system does when we plug that test function into a stochastic integration scheme. So ideally what we want is to pick our scheme and our step size such that the integration scheme has the same stability behavior as the real system. So that was something we had seen in the deterministic case, where if we have a stable system, let's say, we would know that if you want to simulate that with forward Euler, then you need to make your delta t small enough. But if you simulate it with backward Euler, it doesn't matter what your delta t is, and so forth. And we want to do the same thing with a stochastic differential equation. So let's take what we get from our test function, and let's say we use the Euler-Maruyama method. So our test function is what we've defined here. So what then would the Euler-Maruyama iterator look like? X sub n plus 1 is x sub n plus what? Well, we would have a deterministic part, just like forward Euler. So what would be the forward Euler thing that would be contributed by this?
X sub n minus 1?
Yeah, we label it by x sub n. But basically we would have a delta t times omega x sub n. That would be the forward Euler simulation of the deterministic part. And then we've got a stochastic part. So what would the iterator have added to it for that? Well, we would have our noise constant mu times square root of delta t times the 0, 1 normal tangent variable. So that is the Euler-Maruyama iterator for this test function. And then what we would want to do is understand how this is going to behave over successive iterations of the scheme. So if we picked something that should be stable, so something that a test function that falls in this range, are we actually going to get a stable behavior out of our Euler-Maruyama iterator? So we can abbreviate a little and say that this is going to be the growth function we get from the standard forward Euler, so 1 plus delta t omega times x sub n. So this is exactly what we would get if this was just forward Euler, but then we've got this extra thing, mu square root of delta t in 0, 1. And we can look at how that behaves over successive steps of time to understand how this system is going to evolve over a series of steps. So if we start with some initial condition x0, then what is the next value of our simulation going to be, x of 1? As a function of x0, what's x of 1? You know, it's basically we're just plugging in here. It's we've got an x0, 1 plus delta t omega times x0. And I'll just abbreviate here because we're going to need to worry about multiple samples of this. We've got a mu square root of delta t times, I'll call this z sub 1. So z1 is the first of these normal random variables we sample. All right, so then what is x sub 2? What is that going to look like? We're just plugging this thing into this equation here. So what we're going to get is we take this term times this. So we're going to get a 1 plus delta t omega squared times x0. Then we've got this times this. So we're going to get a 1 plus delta t omega mu square root of delta t z1. And then we are throwing in a new noise term, so that would be mu square root of delta t z2. Does that make sense to everyone? All right, so if we keep going, we could say that x3 is going to be now 1 plus delta t omega cubed times x0 plus 1 plus delta t omega squared mu square root of delta t z1 plus 1 plus delta t omega mu square root of delta t z2, and now we have to add in another noise term, so that's going to be mu square root of delta t and a new independent normal z3. And it should be pretty clear at this point what the pattern is as we go forward through successive steps, that in general, as at the kth step, x of k is going to be equal to 1 plus delta t omega to the k, x sub 0, plus sum j equals 1 to k of 1 plus delta t omega to the j minus 1 mu square root of delta t z sub j. And so this then gives us a general statement of what the test function will look like after k steps of the Euler-Mariano method. Does this make sense to everyone so far? So what we want to know is if this thing is stable. So is this thing converging as we go to successively higher k? So is it approaching a constant? Is it approaching infinity? And as I mentioned before, we can't just look at the mean of that process. We need to look at something that captures this kind of random divergence. So what we would generally look at is the expectation of xk squared. And what we want to ask is this thing converging or diverging as we go to large values of k? So this is xk. We want to know the expected value of this squared. So the way we would figure that out is, well, first of all, square it, and then we take the expectation over all of these z terms. So this is going to, in general, have k plus 1 terms in it. So we would get k plus 1 choose 2 terms if we try squaring xk. But it turns out that we can do a lot of simplification that's going to make that a lot easier to evaluate. And in particular, what we can do is consider all of these pairs of terms. So let's say we've got one constant term, and then each of these others is going to be multiplied by an independent unit normal zj. So let's say we take a cross term produced by multiplying the constant term times one of these terms that has a zj in it. What is the expectation of that? So what is the expected value of basically some constant c times a unit normal random variable? Yes, 0. So these unit normals are always zero-centered. The expected value is 0. What about the cross terms where we're multiplying two of these by one another? So in other words, we've got some constant times, say, z1 times z2. What's that? Yeah, this one's actually also 0. So the product of two independent unit normals also has 0 expectation. You can kind of think that it has to be symmetric about the origin, so it's got to have 0 expectation. So basically, when we square this sum here, all the cross terms cancel out. So basically what this is saying is that the expectation of xk squared is just the sums of the expectations of, well, it's the sum of the expectation of the square of each of the individual terms. And we can actually simplify that even more, because what is the expectation of the same normal squared? Well, that's actually 1. So if you square a normal random variable, or a unit normal, the expectation of it is 1. So basically what this means is we can throw out all the cross terms and we can forget about all the z's when we add up the sum here. The expected value of xk squared is just the sum of the squares of the constants in each term of the sum. So in other words, we have the leading term, 1 plus omega delta t to the k becomes 1 plus omega delta t to the 2k, and we multiplied that by x0, so in the expectation of the square of that, this becomes x0 squared, and then we add the square of each of these terms of the sum here. So in other words, what we're going to get is sum j equals 1 to k of 1 plus omega delta t to the 2j minus 2 mu squared times delta t. And that's the expectation of xk squared. Now, so far that is probably not obviously a useful thing for analyzing the stability of this, but we can use kind of one more trick to see why that actually tells us quite a bit about what the behavior of the function would be, and that is to observe that the expectation of x of k plus 1 squared has a simple statement in terms of the expectation of x of k squared. So in particular, the expectation of x of k plus 1 squared is simply 1 plus omega delta t squared times the expectation of x of k squared plus mu squared delta t. So because we're just adding these pairwise sums to get or these pairwise squares to get the expectation of this squared, we end up with an iteration formula very similar to the formula for iterating over successive steps of the unsquared x sub k. Right, so we've now got a statement of the expected value of xk plus 1 squared as a function of the expected value of xk squared. And we should recognize that this is now sort of in a form we've seen previously. In particular, something we saw a couple of classes back when we were analyzing stability of multi-step methods. So if you remember the analysis of stability of the leapfrog method, what we can basically say is that this thing, expectation of xk plus 1, will just abbreviate as y sub k plus 1. And that can be expressed in terms of y sub k as some constant, so this thing we'll call a, so we get a y sub k, plus another constant, which we'll call b, which is this thing. So in other words, y sub k plus 1 is equal to a yk plus b for constants a and b. So this was an example of what we referred to as a linear recurrence relation. And as we had seen a couple of classes ago, we can analyze these things in terms of eigenvalues of a simple linear system. But basically, the solutions to them generally are going to come out in the form y sub k plus 1 is equal to gamma to the k plus 1, where gamma are, and basically plug that into these equations and solve for gamma as the root of a system like this. So in other words, you would have the solution, the gammas that work for this would be the solutions to gamma to the k plus 1, is now a gamma to the k plus b. And that's still not quite trivial to analyze, but the key thing that lets us analyze this is that it turns out that if a magnitude of a plus magnitude of b is less than 1, then we're going to end up with a stable system. So basically, this thing isn't going to blow up unless a plus b is less than 1, which basically lets us determine the stability conditions of this system. And we can say that when we are looking at this Euler-Maruyama method, the system is going to be stable where 1 plus omega delta t squared plus mu squared delta t is less than 1. That basically would be the stability condition for this system. Now in the real system, the stability condition is that the real part of omega plus 1/2 mu squared is less than 1. And it's not quite so simple to state the conditions under which that's true, but basically, if delta t is small enough, then if the real system is stable, Euler-Maruyama will be stable for that system. But delta t might have to be fairly small, but if the real system is stable, small enough delta t will make the Euler-Maruyama system stable. If the real system is unstable, though, then things get a little more complicated. So if omega had a positive real part, would this ever be stable? So delta t is going to be a positive real. So if omega is a positive real, this has to have a magnitude greater than 1. So this squared plus this squared can't be less than 1. So if the system is actually unstable, so if you have an unstable real part, no matter what you do, Euler-Maruyama is going to be unstable. If you have your delta t too big, even if the real system is stable, Euler-Maruyama is not going to be stable. What if we're looking at a real system that is purely imaginary? What will Euler-Maruyama do? What the real part of the system is oscillatory, basically? Or the real system is oscillatory. Well, if the real system is oscillatory, that means omega is imaginary. The magnitude of 1 plus an imaginary has to be greater than 1. So the magnitude of this, the magnitude of real plus imaginary is real part squared plus the imaginary squared square root. So if this thing is imaginary, that's got to be more than 1. So just like with normal forward Euler, this will always blow up if you give it an oscillatory component to the real system. All right, so basically that is kind of giving us at least some guidelines for how we can do the stability analysis. So we can see for the Euler-Maruyama system that this is going to give us a good way of simulating unstable stochastic systems. For stable ones, you need small enough delta t, but because it has order 1/2 strong accuracy, you're going to need a small delta t anyway. But that's just some guidelines for how we can do this. So it is worth knowing that, as I mentioned, these methods are not used so much in biology contexts. In some contexts, physicists use these quite a bit. So you'll sometimes see this referred to as the same thing as stochastic differential equations. And actually, the field where they use this most often is computational finance. So If you really want to learn about these, you basically need to go and learn some computational finance, and that's really where you learn the most about these. But I think they have a lot of potential for biology, so I like to cover them in the context of our other continuous systems. So we're basically out of time here. Are there any last questions before we break?